In the last video, I showed you Kepler's laws of planetary motion, which describe the motion of the planets around the sun, both the shape and the speed, the shape of the orbit and the speed of the planets as they go through these orbits. In this video, I'm going to show you how if we assume that Kepler's laws of planetary motion are true, and we assume that Newton's three laws of motion are true, we can discover what the law of gravitation between the planets and the sun must be. And then we'll go ahead and extend that law to all massive objects. We'll say this force of gravity does not just exist between planets and the sun, but actually exists between any two objects that have mass. So we're going to think about a planet going in a perfectly circular orbit around the sun. Kepler's laws say that not all planets have to move with perfectly circular orbits, but a circular orbit is a type of elliptical orbit, so it will obey Kepler's laws. And it turns out it's easier for us to do these calculations if we think about a circular orbit. This circular orbit has a radius r, and remember that for a circular orbit, the radius is the semi-major axis. So our semi-major axis A of the elliptical orbit is just the radius r of the circular orbit. Okay, so we're saying our planet is going around at some speed v. It has mass little m, sun has a mass big M. First of all, we know that if this planet is going around in this circular orbit at the speed v, well, Kepler's second law of planetary motion says that it has to sweep out equal area in equal time. If the radius is constant, that tells us that the speed v is constant. So the speed of this planet isn't changing. We know that from Kepler's second law of planetary motion. In that case, the motion of this planet around the sun is uniform circular motion. So we know that the force acting on this planet is a centripetal force, Fc. It points in towards the center of the sun, towards the sun, towards the center of the orbit like that. And this centripetal force has a magnitude, F equals m times v squared over r. So now we can use Kepler's third law of planetary motion to think about what would happen to this force as the radius of this planet changes. And we want to see if we can, as the radius of the orbit changes. We want to see if we can write this force just as a function of the radius of this orbit. So Kepler's third law says that t squared is proportional to, in this case, r cubed. So that means that t squared over r cubed is equal to some constant, right? Well, we can relate the orbital period t to the speed v of the planet. We know that the period t is going to equal the circumference of this orbit, 2 pi r, that's how far the planet has to go in order to complete one orbit, divided by the speed, v. So that tells us that v equals 2 pi r over t. So we can write our force here. This equals m times 2 pi r over t squared over r. We can write this as m times 4 pi squared over 4 pi squared r over t squared. Okay, but now we know that t squared is always proportional to r cubed. As we change r, the period of this orbit will change proportional to r cubed. So we can't say exactly what this force is equal to, but we can say that this force is proportional to, well, it's still going to be proportional to the mass of the planet. We can ignore this 4 pi squared because that's just a constant. We're just talking about proportionality. Times r divided by r cubed. Well, this just equals mass of the planet over r squared. So what we've shown by combining together Newton's laws of motion and our formula for centripetal acceleration and Kepler's laws of planetary motion, we've shown that the force, I'm not going to say gravitational force yet, but the force that's keeping this planet going around in a circle must be proportional to 1 over the radius of the circle squared. That is, it must be proportional to 1 over the distance of the planet from the sun squared. Okay, so now we can do one more thing, which is Newton's third law says that if we're going to assume that it is in fact the sun that's exerting this force on the planet. So Newton's third law says the planet must exert a force back on the sun, which is equal and opposite. Since the force of the sun on the planet, big M on little m, is proportional to little m over r squared, well, it makes sense that the force of the little planet on the big planet must be proportional to big M over r squared. The force must be proportional to the mass of the object that the force is acting on. Well, if we combine these together, we find that this force, this gravitational force between the two objects should be proportional to the mass of the little object times the mass of the big object over the distance between the two objects squared. And this is actually the correct form of the universal law of gravitation. The gravitational force between any two masses is proportional to the product of the masses divided by the distance between the masses squared. The only thing that's missing from our formula for the gravitational force is the constant of proportionality. If the gravitational force is proportional to the product of the masses over the distance squared, then we need to include a constant of proportionality. And it turns out from measurements you can determine what the constant of proportionality in Newton's law of gravitation is. We call it capital G. It's Newton's gravitational constant, which is 6.67 times 10 to the minus 11 Newton meter squared per kilogram squared. Okay, what does that mean? Well, one thing it means is that this gravitational force is very weak. 6.67 times 10 to the minus 11 is a very small number. So what this says is if I take two masses, each mass is 1 kilogram, and I put them 1 meter apart, like I've drawn in this diagram here, then the gravitational force between these masses is going to be 6.67 times 10 to the minus 11 newtons. That's a tiny force. That's 66.7 piconewtons, which is an almost, but not quite, unmeasurably small force. So this gravitational force for normal, everyday objects, about a kilogram, about a meter apart, is teeny tiny. In order to get a big gravitational force, you need a very large mass, at least one of the two objects to have a very large mass. So this is why we don't notice the gravitational force, say, between ourselves and the table we're sitting next to, or between one person and another person, because the masses are relatively small, so these gravitational forces are very small. But we do notice the gravitational force between a person and the Earth, or between the Earth and the Sun. These masses are enormous, so they create gravitational forces that are noticeably large. So this formula here, F equals G m1 m2 over r squared, works for any two masses. And this force is always attractive. That is, mass 1 always pulls on mass 2, and mass 2 always pulls on mass 1. These two forces point directly from one mass to the other. We can represent this all with a single vector equation, which says that this force, the force vector, equals G times m1 times m2 over r squared times r hat with a negative sign. So r hat, well, we learned about unit vectors, I hat, j hat, and k hat. R hat is a unit vector that points from mass 1 to mass 2. If we have some vector r that points from m1 to m2, we can always find the unit vector, which just has a length 1 but points in the same direction. We can always find the unit vector r hat by just taking r hat equals r over the magnitude of r, we take the vector r and divide it by its own magnitude, and this gives us a vector with length 1 that points in the direction of r. So this is the full vector form of Newton's law of gravitation. Notice that if I switch m1 and m2, I just switch the direction of r hat. So instead of pointing from m1 to m2, r hat points from m2 to m1, which switches the direction of the force, and therefore this vector form of Newton's law of gravitation automatically obeys Newton's third law of motion. That is, that the force that m1 exerts on m2 is equal and opposite to the force that m2 exerts on m1. Now, for the most part, I'm not really going to use this vector form of Newton's law of gravitation. It's a little bit clunky to actually always have to calculate what r hat is. Sometimes it's useful. Usually what I'm going to do is use this form to calculate the magnitude of the gravitational force, and then I will just figure out what the direction is. I know the direction always has to point from one mass to the other mass. Let's do a quick example to start with. I want to calculate the gravitational force acting on an 80 kilogram person standing on the Earth's surface from the Earth, which has a mass of 5.97 times 10 to the 24th kilograms and a radius of 6,371 kilometers. The moon, d is the distance of the moon from the Earth, and the sun, where d is the distance of the sun from the Earth. Okay, so first, here is the Earth, and here is a person standing on the Earth. So for part A, we know our formula is F equals g times the mass of the person times the mass of the Earth divided by r squared, where r is the distance between the person and the Earth. But what do we use as this distance? If the person is standing on the surface of the Earth, that distance is very short, but the distance between the person and the opposite side of the Earth is very far. Well, if we were to go through and do this problem correctly, what we would do is say, okay, here's a little chunk of the Earth over here. We'd calculate this distance r, say r1. We'd say this chunk has a little mass m1, and we'd calculate the force between the person and that chunk, and then we'd integrate that force over the whole Earth. So this would be a three-dimensional volume integral, and it's a big pain to do this. But it turns out if we do that, we find that the force acting on this person is identical to what we would have if we calculated the force between the person and a point particle with mass m at the center of the Earth. So we can just use the radius r of the Earth as our distance between the person and the center of the Earth. And this actually works for any spherical object. If I want to calculate the gravitational force exerted by a spherical object on something else, I just have to calculate the distance between that spherical object's center and the other object. So this works for planets, for any kind of spherical object. It makes our lives a lot easier. So when we're talking about the Earth or any other spherical object, we can just use the radius of the Earth if we're standing on the Earth, or if we were out here, we would use this distance from the center of the Earth to the point where we're calculating the gravitational force. So I'm going to go ahead and plug in my numbers to figure out what this force is. But first, I'm going to do something. I'm going to write this force as g times m over r times the mass of the person. And I'm just going to calculate what g times m over r is. Well, this equals, so I'll leave out my little m here, times g, which is 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared, times the mass of the Earth, 5.97 times 10 to the 24th kilograms. And then I can divide this by r, the radius of the Earth, squared. Sorry, these should be squared. which is 6,371 kilometers. So I need to put this in meters, times 10 to the third meters squared. Okay, so when I plug this all into my calculator, what do I get? Well, I get 9.81, and let's check what my units are. My units are, well, I have newtons, I have meters squared, cancel meters squared down here, and I have 1 unit of kilograms in the denominator, canceling kilograms. So I have 9.81 newtons per kilogram times the mass of the person, m. Well, remember, a newton is a kilogram meter per second squared. So this equals 9.81 meters per second squared times m. Well, this 9.81 meters per second squared, that's just the acceleration of gravity. So it turns out that for a person standing on the surface of the Earth, we do get 9.8 meters per second squared, just the acceleration of gravity, and their weight is just mg. Exactly what we were using earlier in the semester. But this law explains why the weight of a person is just mg. It's because of this law of gravitation, and g remains the same. For every person on the surface of the Earth, the mass of the Earth is the same, the radius of the Earth is roughly the same. So g is always going to be about 9.8 meters per second squared. So now we can plug in our mass here. This is 80 kilograms times 9.81 meters per second squared. And we find that the weight of a person is about 785 newtons. Okay, that's the gravitational force acting on a person. So what's cool here is that I can now use this formula here to calculate the acceleration of gravity at the surface of any planet. If I know the mass of the planet and the radius of the planet, I can find the acceleration of gravity on its surface. Because this law of gravitation works anywhere. It's universal. Works everywhere in the universe. Whereas mg, well, the g here depends on what planet I'm on. So now for part B, we want to calculate the force between this person and the moon. Well, the distance of the moon from the Earth is about the same as the distance of the moon from this person. Depends on exactly where on the Earth the person is, but the radius of the Earth is small compared to this distance of the moon from the Earth. So we can just say that the force of gravity from the moon equals g times the mass of the moon times the mass of the person over d squared, which is then equal to 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared times, actually move this down to the next line. This is times the mass of the moon, which is 7.35 times 10 to the minus 10 to the plus 22 kilograms times the mass of the person, 80 kilograms. And then I divide all of this by the distance of the person from the moon, which is 384,400 kilometers, so times 10 to the third meters squared. Putting that all into my calculator, I get 2.65 times 10 to the minus 3 newtons. So, while the gravitational force of the Earth on this person was 785 newtons, gravitational force of the moon on this person is 2.65 millinewtons. That's teeny, teeny, tiny. Very small. The moon exerts a negligibly small force on any person on the Earth. And for part C, I'm not going to go through this whole calculation again. I'll just give you the answer that the force that the sun exerts on a person, I calculate this exactly the same way that I did with the moon, is 0.47 newtons. It's a little less than half a newton. And this force actually keeps us, this force that's acting on us from the sun, keeps us going in orbit around the sun along with the rest of the Earth. So the gravitational force from the sun is much smaller than the gravitational force from the Earth on a person, but much bigger than the gravitational force from the moon. So this just gives you an idea of how to calculate these gravitational forces and sort of how important these different masses are in terms of the total gravitational force acting on us. Note that the sun, it is very far away, 149.6 million kilometers, but it's also enormous. 2 times 10 to the 30th kilograms. That's a very, very big mass. Whereas the moon is much closer than the sun, but has a much smaller mass, so it ends up exerting a smaller force. Now let's do a more interesting example. We know how to calculate the gravitational force between any two objects, but what happens if we have more than two objects? Say we have 3 masses here, M1, M2, and M3, and they're on the corners of a right triangle with side lengths of 1 meter. And we want to find the magnitude and direction of the force acting on M1. Well, here's how we do something like this. We would calculate 2 forces. There's the force that M2 exerts on M1, which looks like this. Let's call that F21. And there's the force that M3 exerts on M1, which looks like this. Let's call that F31. The net force is going to be the vector sum of these 2 forces. The net force acting on F1 looks like that. And we could repeat this for the other 2 masses if we wanted. We know from Newton's third law that M1 exerts an equal and opposite force back on M2, so this would be F1, F12. M3 exerts a force in this direction on M2, F32, and M2 exerts an equal and opposite force back on M3, F23, and finally M1 exerts an equal and opposite force on M3, F13. So those are all the forces acting on the system. And if we want to find the force on a particular mass, we just add up the other 2 forces acting on that mass. So in this case, we're just going to do this for M1. So first thing we have to do, F21. Well, let's first calculate the magnitude of this force. F21 is going to equal G times M1 times M2 divided by the distance between M1 and M2, which is L squared. So if I plug my numbers into this, I get G is 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared times M1 is 1 kilogram, M2 is 2 kilograms, and then I divide this all by 1 meter squared, and I get that this equals 1.33 times 10 to the minus 10 newtons. And this vector, well, I can see it points straight up. So in this case, it's pretty easy. I just multiply this by j hat to find the vector direction of that force. I do the same thing for F31. This equals Gm1 m3 over L squared. And when I plug my numbers into that, I find that this equals 2.00 times 10 to the minus 10 newtons. And my direction for F31, well, it just points to the right in the positive x direction, so I'll call this I hat. Okay, so I have my vectors F21 and F31. My net force on M1, F1, equals F21 plus F31, which equals 1.33 times 10 to the minus 10 newtons j hat plus 2.00 times 10 to the minus 10 newtons I hat. Okay. Now, if I want to find the magnitude, well, I just use the Pythagorean theorem. The magnitude of F1 is going to be equal to the square root of F1x squared plus F1y squared. This just equals 2.40 times 10 to the minus 10 newtons. So that's my magnitude. And my direction, I can find, well, this is the angle, let's say it makes with the horizontal direction. It is the inverse tangent of F1y over F1x, which equals 33.6 degrees. Okay, so that's how you handle a situation like this with multiple masses. We say that the gravitational force obeys the principle of linear superposition, which just means that the force from different masses add as vectors, just like any other force would. Now, this example I did here was relatively easy. Why was it easy? Well, because F21 and F31 are already perpendicular to each other. I didn't have to break them up into x and y components. But if I wanted to calculate the force on M2 or the force on M3, I would have to take these F32 or F23 forces and break those forces into x and y components. So what I would do is first calculate the magnitude using Newton's law of gravitation, and then I would break that up into vector components using sine and cosine functions. So this is the kind of thing you'll need to do on your homework on gravitation.